All right, let's start with this problem, which is very interesting. This was sent to me by my friend, and I thought it's really a good one to discuss with all of you. Take a moment and read the question. Try to solve it on your own. If you cannot solve it on your own, then resume and watch the tutorial. Right? That would be my suggestion. Okay. Before you actually watch the complete tutorial, make sure that you've tried it properly to solve it on your own, right? Otherwise, let's go ahead and solve it. Two particles, each of mass 3 kg and having charge q 10 microcoulomb connected by a massless string of length L equals to 10 centimeter are placed on a frictionless table as shown in the figure. If the midpoint of the string is moved with a constant velocity of v equals to 3 meter per second in a direction perpendicular to the initial direction of the string, then the minimum separation between the charges will be what? Okay, that's what the question asks. But let us first use the standard approach to any mechanics problem. First of all, have a good understanding of the overall motion and then try to find out which part of the motion do we need to really focus on. So let's understand this. First of all, let's take this, the x-axis and y-axis setting, right? So this is x and this is y-axis. Right, in this, the string is like this. The center is at O, and the entire length of the string is L. It's given, say, given like right. So here is a particle, here is a particle. They both have charges Q and Q, masses M and M. Right. In that case, what will happen? Okay, initially when there is nothing has been disturbed in the setting. So what happens is the just look at the symmetry of the problem. You will understand that whatever the motion of the left is, that would be mirrored symmetrically on the right. Okay, so basically it's a mirror symmetry. Whatever the motion happens in the left, the mirror symmetry happens on the right. Let's just focus on one particle. So this particular particle on the left is being pushed by Coulomb's force, okay, to the left, and it is getting pulled by the tension to the right, correct, along the x-axis, right? This is the x-axis. You can, since everything is in equilibrium, you can just equate Fc equals to T and find the value, and you can find the value of Fc at this in the beginning to be K, Coulomb's constant, Q squared by the mutual separation, which is L squared, correct? But then what happens after some time, once you start to move the center with a velocity v, constant velocity v, what will happen? That the string would no longer be in along the x-axis. It will have some angle theta, correct? So this will be the particle m and q, right? And then this is going to be your y-axis. So the tension will be like this, and it will have a component which is t cos theta, and fc would keep on being on the left, to the left, and it will lie always along the x-axis. But but what will happen is the value of t cos theta would increase more than fc, so the particle would you know move towards the right. So the same thing is going to happen to this particle also. It is going to move to the left, and there will be a point where this particle will come to rest. Why? Because it started with zero. It will, because the net force is towards the right. It will start to move towards the right, so it will have an acceleration, and gradually as it comes closer to the right charge, as the mutual separation keeps increasing, the Coulomb's force would increase, such that at a stage where the tension, the component of tension uh, to the to the right would be balanced by the Coulomb's force to the left, right, for each particle, okay, on this particle. So the particle would have no net force, right? No net force, but then it will have some velocity, so it will keep on increasing. It will keep on moving to the right. Once it does, FC would keep on increasing again. Okay, FC would actually increase beyond the component of tension, so it will resist the velocity. there will be some acceleration which will be variable, okay, and not a constant acceleration, but it will reduce the velocity so that at a point where the velocity would be zero. At that point, the particle on the right would also be similarly placed. So this separation would be something that we need to find out. We need to find the value of d. So that is all we need to find in this problem. All right. So there is something that we need to understand also, that how the particle would move beyond the closest approach. Once the closest approach has been placed, okay, once the closest approach has been achieved, the particle would start to move to the left. Why? Because Coulomb's force is still more than the tension, horizontal component of tension. So it will move towards the left and come back to the same separation as it was, like the same L by 2, correct? That is when it will come to the rest. So it will be basically moving like a pendulum, right? Okay, the same part here also, it will be moving like a pendulum on the right. But then this is about the x-axis. What happens to the y-axis? In the y-axis, the tension, if this angle is theta, this is the x-axis, this angle is theta. So this angle is theta. So the tension will have a component t sine theta along the y-axis. And there is nothing that balances t sine theta, right? So the particle would be accelerated in the y-axis till what happens? The string becomes like this. String goes to a theta like this, and there will be some velocity on of this particle, and now the tension would basically the would have an x component which is going to be opposite in direction to the velocity of the particle. So what will happen if you look at the situation? This this particles would basically, like, if you look from the frame of reference of point this point of the center O, this particle would start from here, come here, and then go back here, come here, and then go back here, come here, and go back here, come here. This is how it is going to happen. And similarly, the mirror symmetrically, this side would also be moving like here and here and here and here and here and here. So this separation is what we need to find out. Okay. So now we have an understanding. So this is very similar to the problem that we see for a vertical circle. For example, so circle in a vertical plane, a particle is hanging in a string like this. If you give a tangential velocity to this particle at rest initially, you suddenly give it a tangential velocity. Gravity is downward. It will go up to certain height, right? It will rise up to certain height and come to rest, and then fall back to its mean position. Then in the opposite direction, it will rise by the same angle theta and to some height. So basically, people ask by what height the particle rises, correct? By what height the particle rises in the vertical direction. But here the problem is, in our case, the problem is okay, in this vertical circle problem, g used to be constant, so it was a very easy calculation, right? Just apply the energy, kinetic energy, and work energy principle. You solve it. But then here also we can do the same thing, but then here the acceleration is not constant, right? So just focus on the motion on the x-axis. So what we're gonna do? Let's say just take the one half of the particle, one half of the arrangement. Okay, so the separation is L by 2, correct? So now let's say that this angle is theta, correct? If this angle is theta, let me draw it in a larger one. Might be, it might be a little. So let's see that this is the part of the string, correct? Okay, let's or put the axis also. Let me draw it properly. We and y-axis. Right. So in this case, this is the x-axis, this is the y-axis. So now the string, let's just imagine the left half of the string, correct? Half of this after some time. Okay. And initially, the left half of the string was like this. Okay. See, it was lying along the, this is the origin. Okay, this is where it was, and this is where it is now. It has gone through an angle theta, right? Okay, this is how it has moved. Now here, if you take this point as the reference origin, if your frame of reference is fixed on the origin, then if it is moving with a velocity v, then instead you will find that this particle is moving with a tangential velocity v, whereas this separation is L by 2, correct? The total length of the string is L. So now what will happen is, right, there will be some tension in the string. Okay, some tension. This tension is not going to do any work because it is, and this particle here, it is confined to move in a circle. Okay, it is confined to move in a circle, correct? Because it is tied to the string, assuming that the string remains constant. Otherwise, it will be a very hard problem to solve. If the string remains stretched all the time, the particle is going to describe a circular motion. Okay, so in not exactly a complete circular motion, its path will be a circle. So in a circular path, the tension does no work. So only work is done by the Coulomb's force Fc. So let us suppose that while doing so, if it has moved by a distance, whatever distance it has moved by some distance x. So it will be doing some work, correct? And since it is doing some work against the Coulomb's force, it will lose some of its kinetic energy. So what is its initial kinetic energy? It's half mv squared, right? So when it gradually comes to a point where it is zero, its velocity is zero, sorry, its kinetic energy would be zero. So the net change in kinetic energy is half mv squared. That is the energy that it would, spend in doing some work against Fc. So what is the work done? So let's say at any distance, okay, if it is at a distance, where exactly is it? It's at minus L by 2 initially. Let's suppose it comes to a point which is minus d to the left. Similarly, the other point would come to the x coordinate d, while it was initially where at L by 2, right? We just solve for the left, we will find the answer because we need to find the value of, basically it's minus, let's call it minus d by 2, it will be d by 2. Okay? So we need to find the value of d. What is the value of d? So as it moves from minus L by 2 to minus d by 2, it basically does work against the Coulomb's force. So let's say if it as it moves, the Coulomb's force would also vary, correct? So let's say that at any distance, at any point minus x, or let's say at any point in the left hand side, at any point minus x, right, if it moves a distance dx, and the direction of dx is going to be positive, okay, in this direction, okay, in this direction, dx is going to be positive because it's along the positive direction of the x-axis. So what is the value of Fc at that point? Fc at any distance minus x for the left particle is k q squared divided by the mutual separation between these two particles, right? The other particle will also be at x. It will be minus x. This is as x. The mutual separation is what? 2x. So it's going to be 2x squared, correct? So that, but the force would be on the left. The force on this particle would be to the left. It moves a distance dx. So work done, work done by the Coulomb's force is going to be in integration Fc dot dx while it moves from minus L by 2 to minus d by 2. So that is the work done by the Fc. Okay, work done by Fc. but then work done by the particle would be work done by the force. But the work done by the particle would be negative of that, correct? uh, Actual work done by the particle would be less. So let us say that it is minus again Fc and dx are totally opposite, correct? So 180-degree separation. The dot product would have a negative sign, and that negative sign would come outside the integration, and eventually it will be cancelled. Correct? Right. So it's going to be integration a q squared by 2x squared will be 4x squared times dx, right? And the limits would be minus L by 2 to minus d by 2, right? So it's going to be what? K q squared by 4. That's the constant part. And integration of dx upon x squared minus L by 2 to d by 2, correct? So if we do it again, it's going to be k q squared by 4, and the integration would be like dx by x squared will be minus 1 by x, correct? Minus 1 by x, so it's going to be minus 1 by x within the limits of minus L by 2 to minus d by 2. So how do you put these things in order? It's going to be like a cube squared by 4, uh, the parenthesis minus 1 by minus d by 2, right? Minus minus 1 by minus L by 2, correct? So it's going to be k cube squared by 4. Make sure that you're using the signs very carefully here, otherwise you might make a mistake, right? A squared by a cube squared by 4 times gonna be 2 by d, right? So the 2 will go up, and then minus minus minus, it's gonna be minus 2 by L, right? So the 2 comes out as the common factor. It's gonna be k squared by 2 times 1 by d minus 1 by L, right? And that is going to be half mv squared, right? That's going to be half mv squared, because that's the loss in kinetic energy, right? So in that case, what you're going to do, you need to find the value of d. So how will you do it? The half and 2, they will cancel out, so it's going to be k squared aq squared, here will be L minus d by LD is mv squared. So it's gonna be kq squared L minus k squared d, which is mv squared LD. Now take the d terms together. You're gonna have like mv squared LD plus kq squared d is kq squared L. So now you just take the d as common factor, mv squared L plus kq squared, which is kq squared L, right? Now the value of d is going to be kq squared L upon mv squared L plus k squared. Now how do you find the value of this one? Just put in the values, plug in the values in SI unit, okay? Let's see, what is the question that was asked, in which unit do we have? Okay, everything is in centimeter, but to do the calculations again, what I'm gonna do, I'm gonna convert everything to SI unit and then convert back to centimeter. So 10 microcoulomb, 10 centimeter, 3 and 3 kg. Okay, 10 micro. So here I'm gonna put k. The value of k is 9 times 10 to the power 9. I know this is an SI unit, so everything has to be an SI unit. A q squared. What is q squared? Q is 10 microcoulomb, right? So 10 microcoulomb. 10 microcoulomb is 10 to the power minus 5 coulomb, correct? It's going to be 10 to the power minus 5. If you square it, then it's going to be 10 to the power minus 10. 10 to the power minus 10 multiplied by L. What is the length L? L is what is the value of L? L that we have is 10 centimeter, correct? 10 centimeter is like what? 10 into 10 to the power minus 2 centimeter, which is 10 to the power minus 1 meter. To the power minus 1 meter, correct? So, and then we divide it by mass, which is kg, 3 kg, and the velocity is what? The velocity is 3 meter per second square, so it's in SI unit. It's going to be 9 times, again 10 to the power minus 1, that's the length, plus 9 into 10 to the power 9 times 10 to the power minus. So when you solve it, it's going to be what? 9, let's, you know, sum of the powers. This is like 10 to the power 9 the power minus this 9 times 10 to the power minus 2. Okay, it's going to be minus 2. 9 times 10 to the power minus 2. Minus 11, 9 minus 2, yes, divided by the, it's going to be 3 times 9, 27 by 10 is 2.7 plus, it's going to be 9, 10 to the power 9 into minus 10, so it's 0.9. I can just simply write this as 9 into 10 to the power minus 2, 0.009. I can just write it as 0.0 and write it as 0.09. 9 into 10 to the power minus 2, 3, 1, 2, 0. Yeah, correct. So let's see what is this. It's gonna be 0.09 divided by what is 2.7 and 0.9, 3.6, 3.6. So it's gonna be 3.6. So what do you need to do? Multiply 100 to the numerator and the denominator. So it's gonna be 9 by 6, 0, correct? 1, 2, 1, 2, correct? So it's gonna be 40, 1 by 40. What is 1 by 40? 1 by 40 is 1 by 40 is 1 by 4 divided by 10, correct? That's 0.25 divided by 10, which is 0. Which is 2.025. What's that meters? How many centimeters would it be? 2.5 centimeters. That's going to be the answer. Value of D. So the correct option is B. Okay, the calculation was a little long. Otherwise, you could have done the calculations. Get a second. Let's go ahead and solve the second question. Watch the next video.